just about to get started. So as I mentioned just now, we're going to be looking at LU factorization today. This is chapter 7. I think leaders probably told you this, but this term is going to be a lot gentler than last term. So we kind of like worked you hard last term. So now I'm not saying you could relax. I'm just saying sort of, hopefully you'll find it a bit less stressful. Okay, so what we're going to be looking at this term in my half of this unit is solving linear systems. Now, why in an ordinary differential equations unit are we solving linear systems? Well, the reason being we often need to solve linear systems within our methods. Okay, so the implicit Runge-Kutta methods will require solutions to linear systems. If you use any finite difference methods, which you did for the assignment last term, part of that was solving a linear system. Okay, so that's what we're going to be looking at. Just to remind you, a linear system is of this form. Okay, just a number of equations. Your unknowns are x1, x2, x3. That's what you're trying to solve for. They may have coefficients, which are the a values, and they're all equal to some quantity on the right-hand side, b. Okay, this is a linear system because none of the unknowns are raised to any other power apart from 1. Okay, hence it's a linear system. And you've seen in previous studies in the subject, but we tend to write linear systems in a matrix equation form. Okay, so this square matrix here is what we call our coefficient matrix. Okay, on the right-hand side, we have our vector of b values, so our right-hand side vector, and vector of x values, that's what we're trying to find. We're trying to solve for x. So a's and b's will be given to you, they'll be known, they'll be values. X's will be your unknowns, and that's what we've got to solve for. Okay, so in this term, we're going to be looking at 2 different classes of solution methods. One called a direct method, which we're going to start off this week and in a couple of weeks, and the other is called indirect methods. Okay, so the first direct method, well, you already know one direct method, Gaussian elimination. That is an example of a direct method. Okay, so we're going to be looking at LU factorization. Now, LU factorization uses elementary matrices. Have you seen these before? You seen them last year with Steve? Perhaps not. Okay. Well, with do you remember Gaussian elimination? What's the process of solving a system by Gaussian elimination? Maybe you tell me what we do. Sorry? Row reduction, yeah, we have row reduction. Okay, so we reduce your matrix to row echelon form, and to do that, use row operations. Now, there are 3 different types of row operations you can use. Okay, so we got the first type, type 1, which means we permute, in other words, swap any 2 rows. So that's the first type you can do. That's type 1. Type 2 is you can multiply any row by a number. Okay, and the third type is you can add a multiple of another row to a current row. Okay, these are called elementary row operations, or ERO. Okay, what you can do is we can actually express an individual elementary row operation as a matrix. Okay, and this matrix are called elementary matrices. So what we do is an elementary matrix is one of these row operations applied to the identity matrix. Okay, so if we permuted row I and row J, we're going to end up with a matrix which is the identity matrix, but with 2 of their rows swapped. Okay, and we're going to call this matrix P subscript ij. Okay, so P is our matrix. It's going to be a square matrix. I and J are just the row numbers. Okay, so that means we swapped row I and row J around. If we multiplied one of our rows in the in the identity matrix by a number. Okay, we're going to express this in this notation. So M for multiply, I is the row we've multiplied, and K is the number we've multiplied by. So P is simply a matrix, Pij, that's the identity matrix with rows I and J swapped around. Mik is the identity matrix with the row I multiplied by the scalar K. The third type is adding K lots of row J to row I. Okay, and with add, we take A, we add, we take row I and add K lots of row J to row I. Okay. So an elementary matrix is simply a row operation applied to the identity matrix. The tricky thing is the notation. So P for permute, M for multiply, A for add. Okay. And the reason why we use these in this method is pre-multiplying a matrix by an elementary matrix has the equivalent effect of performing that row operation. Okay, so if you, let's say you swap two rows, okay, well, if you pre-multiply a matrix by Pij, that has the same effect of applying or swapping those two rows. Okay, as always, it's a lot easier to see an example. Okay, so let's take a 2 by 2 identity matrix. What are all the possible elementary matrices? Okay, so at the top, we can swap rows 1 and 2 around. So if you take the identity matrix, swap row 1 and 2 around, we get this. We can multiply row 1 by K, we get this. Or we can multiply row 2 by K. We can add K lots of row 2 to row 1. Okay, this is sort of the trickiest, the Aij one. So this means take row 1, add K lots of row 2. Okay. And also, or vice versa, you can take row 2 and add K lots of row 1. Okay, so those are all the elementary matrices for a 2 by 2 matrix. Obviously, 3 by 3, there's going to be more of them. Okay, a nice thing about elementary matrices is it's dead easy to calculate their inverses. Okay, so the inverses, if you swap two rows, the opposite operation is just to swap them back. So if we've swapped rows I and J around, to undo that, the inverse is just to swap them back. Okay, so Pij inverse is simply Pij. If we multiplied a row by K, to undo that, we simply multiply the row by 1 over K. So the inverse of Mik is simply Mi 1 over K. Okay, and if we added K lots of row J to row I, to undo that, we simply subtract K lots of row J from row I. So the inverse matrices of an elementary matrix is quite simple. For permuting, it's just the same. For multiplying, it's just a reciprocal of K. And for adding, it's just minus K rather than plus K. Okay, and those are all the inverse elementary matrices. Okay, so why have I gone through talking about elementary matrices? Well, LU factorisation requires knowledge and use of elementary matrices. So that's what we're going to be looking at now. Okay, quite a lot of this stuff, it's sort of presented in quite a formal manner. Don't get scared off by this. Okay, so I've presented it as a theorem and a proof. As soon as we start to have a look at some examples, I hope you'll see, but it's actually not that scary at all. Okay, so what we can do with elementary matrices is we can chain them up. Okay, we can multiply elementaries, but we can calculate a product of several elementary matrices to give us a matrix A. Okay, so if we have a matrix A and we apply, let's say, K row operations. So we have k number of elementary matrices. If we multiply them all together, okay, we get the inverse of A. Okay. So E1 is an elementary matrix corresponding to the first row operation I applied to A. E2 would be the second row operation which I applied to A, and so on and so forth. Okay. So the inverse of A is calculated by the last row operation multiplied by the penultimate one, etc., right the way down to the first one. Okay. We can calculate the inverse of A quite simply. A is, if we reverse this sequence here, and we find the inverse of the elementary matrices, okay, we can go upwards. Okay, so that's the first row operation, inverted, multiplied by the second row operation, inverted, etc. Okay, let's show you a proof of that. Well, by definition, okay, if I row reduce A to reduce row echelon form, that means I apply row operations until I get the identity matrix. Okay, I've assumed it's going to take me take me k row operations to do that. Okay, so if I apply the first row operation to A, then apply the second, and ek is the last row operation. By definition, that would give me the identity matrix. Well, since the inverse of A times A is the identity matrix, then all of these, which I've multiplied by A, should be A inverse. So that sort of proves the second one. Okay. If that's A inverse, all I do is invert the elementary matrices. Okay, so remember, when you invert the product of matrices, you reverse their order as well as inverted. And this gives you A. So that's a quick proof of how we can calculate A and A inverse using elementary matrices. Okay, let's have a look at an example. Okay, I've got a 3 by 3 matrix A here, and we're going to express A and A inverse using elementary matrices. Okay, so what I'm going to have to do is row reduce A until I get to the identity matrix. Okay, this is going right back to your first year stuff, Gauss elimination. Here, just to remind you, we start off with the pivot element of row 1, column 1, which is 0. I've got a problem there. Okay, I can't do anything with 0, so I'm going to have to do partial pivoting. Well, actually, here I haven't done partial pivoting. I've just done a row swap. Okay, so if I swap row 1 and row 2 around, by the way, this is the sort of notation I use. I don't know whether it's similar to what you've seen in the past. Tilde means sort of this gives. Okay, so if I swap row 1 and row 2, okay, it's quite simple to do. Now, so 1 is my pivot element, and I need all the values below 1 to be 0. Okay, so in row 2, I've already got 0, so that's good. In row 3, I've got -2. Okay, so how do I get -2 to go to 0? Okay, using row 1. Okay, so I'm going to use the pivot row, and I need this -2 to be a 0. Well, 2 lots of 1 gives me +2, and if I add -2, I get 0. Okay, so essentially what you're multiplying row 1 by is -2 times 1, and you normally subtract that. So row 3 minus -2 over 1 gives me this here. Okay, and as you can see, I have zeros underneath. Okay, I need to make this, so that's my first pivot row done. My second pivot row, okay, this is a pivot element, -4. I need to make that to be a 1, so I'll multiply it by -1/4. Okay, now, because I'm going to reduced row echelon form, I need this -1 above to go to 0. Okay, so I want to end up with the identity matrix. So to do that, if I add row 1 and row 2 together, that'll go to 0, and I get this matrix. Okay, so now my pivot element is 8. So if I take 1/8 of row 3, that changes the pivot element to 1. Apply row operations to the 2 rows above, and eventually I get down to the identity matrix. So that's reduced row echelon form. Okay, so sorry, which one? Yeah, that one there. Yep, should be +1/2. Sorry, which one? So from this line, so it's never changed, does it? It's typo. Yeah, so the typo's in the matrix, not in the row operation. Yeah, sorry about that. The typo's in the matrix, not in the row operation. Same in your notes. I just done a copy and paste job. Okay, so to express A as a product of elementary matrices, what we do is we inverse the elementary matrices and write them down in the order they were applied. So I'm going to sort of flip backwards and forwards between slides here. So the first thing I did was permute row 1 and row 2. Okay, inverse of permuting row 1 and row 2 is just permuting row 1 and row 2. So that's the first elementary matrix. Second thing I did was add 2 lots of row 1 to row 3. So here, if I inverse that and subtract 2 lots of row 1 to row 3, I get A31 minus 2. And if I keep going, okay, so these are all the inverses of those row operations. Okay, if I multiply them all together, okay, that gives me A. And if I was to write them out, okay, this is what you get. And now this is rarely done. This is not what we normally do. I've only done it just for demonstration purposes. If you were to write them all out, multiply them together, takes you ages. That will give you A. What about A inverse? Well, A inverse, we list the elementary matrices in the reverse order that they are applied. Okay, so the last thing we did was subtract 1/2 lots of row 3 from row 2. So that goes first. Then we subtracted 7/2 lots of row 3 from row 1. So that comes next, etc. So I can calculate the inverse of A by finding the product of all those matrices, and that will give me A inverse. Again, not particularly useful, but the point of showing you this is we're going to use it in LU factorization. Okay, what I'm going to do is just I'll do a quick example. I want time getting on, so I don't want to do too much. Okay, so by the way, on these notes on page 86, okay, where I've got worked examples, you know I've left a load of space. It's kind of like you're meant to fill it in. Okay, so what I want to do is I want to row reduce this to reduce row echelon form. Okay. So what's my first operation? What am I going to do to get this to be 0? Yeah. So that'll give me 1, 2, 0, minus 2. Okay. By the way, what I can do here, there's not a unique solution to this question. Okay, depending on what row operations you use, you'll get a different answer. Doesn't mean it's wrong. So what I could do now is I could either multiply the second row by minus 1/2, or I could add row 1 to row 2. I'm going to add row 1 to row 2. I'm going to say row 1 plus row 2, because in doing so, that goes to 0. Okay, finally, to get minus 2 to be 1, I multiply by minus 1/2. Okay, So if I wanted to write down the original matrix A as a product of elementary matrices, what I do is I take the row operations I applied. So the first thing I did was row 2 minus 3 row 1, invert it. Okay, so I've added minus 3 lots of row 1 to row 2, but I'm going to invert that in a minute. The next thing I did was I added 1 lot of row 2 to row 1, and that's going to be inverted. And here I multiplied row 2 by minus a half. So M2 minus 1/2, that's going to be inverted. Okay, so if I invert these, remember these are dead easy to do. All you do is when you add Aij k, the inverse is Aij minus k. So that's the same as saying A213, A12 minus 1, and M2 minus 2. Because when you multiply, you just simply, instead of k, I go 1 over k. Okay, so that's A. Okay, to calculate A inverse, what I do is I look at the last thing that I did to my matrix. What was the last operation I did? Well, that was M2 minus a half. Okay, what was the next one to last? Well, that was A12 plus 1. And the first thing I did was A21 minus 3. Okay, so that just shows you can, if you were to write out those matrices, multiply them all together, you should get back to A, and you should also get A inverse. Okay, what I'm going to do now is, I know there is a second example down here, but I'm just sort of wary of the time. So I'll leave you to do that in your own time, and I'll put up scans of the solution afterwards. Okay, that's elementary matrices. This brings me on to what I really wanted to cover today. Okay, this is a method of LU factorization. Now, this is a method of solving linear systems. Okay, so it's a procedure for factorizing a matrix A, and what we do is we factorize it so it's equal to the product of a lower triangular matrix L and an upper triangular matrix U, hence LU. Okay, so what I'm going to do is I want to calculate L and U such that L is this matrix. Okay, so L is lower triangular. Okay, so all the upper triangular elements are 0. On the main diagonals, I have 1. Okay, so for L, the main diagonal elements are all 1. The lower triangular elements I have to determine, or we have to determine. For U, okay, the lower triangular elements are all 0, and the upper triangular elements we've got to determine. Notice for the main diagonal for U, we may not have 1s. Okay, L, the main diagonal, always 1s. Why do we want to do this? Well, if we factorize a coefficient matrix using LU factorization, then we can solve a linear system easily by using forward and then backward substitution. So we can change the values of our right-hand side vector. It won't change L and U. So once you factorize to L and U, you can change the values on the right-hand side and solve. So it's useful, for example, for things like finite differences. Okay, so what's the process? I've given you the theorem here without proof. I think I've given you a proof of it in the notes, but it's if you should take time just to read the proof afterwards. Okay, so let's say we have a coefficient matrix, and we've applied k elementary matrices. So we've done k row operations. And we got it to row echelon form. Okay, we don't have to go to reduced row echelon form. We just need it so that our coefficient matrix is an upper triangular matrix. Then we can write U as the values of the elementary matrices applied in reverse order. Okay, so that's the first one we applied. That's the second one, and EK is the last one. So that gives us U. L, what we do is we reverse all of our elementary matrices, and then calculate the inverse. By the way, U will just be what we get left over at the end of the row operations. So you don't actually have to apply this. But what I like to do is I like to write it out, because then it helps me when I'm doing L. And you can see the lecture notes for a proof of that. Okay, so let's have a look at an example. So here we've got a 3 by 3 matrix. Okay, we're going to calculate the LU factorization of this. First thing we do, row operations to reduce to row echelon form. By the way, with LU factorization, you're not allowed to permute two rows, and you're not allowed to multiply a particular row. With LU factorization, you can only use adding of another row. Okay, so we'll come on to another method which can allow for permutations. Okay, so we're only allowed to add the quantity of another row. So essentially, that's what the row operations are. I'm not going to go through too much detail. I think you're quite familiar with this now. Okay, so this gets me down to row echelon form. In other words, I have an upper triangular matrix, and all my lower triangular values are 0. That's my U. That is my U matrix. And that's easy to find U. Okay, so what did I do? Well, the first thing I did was add minus 2 lots of row 1 to row 2. The second row operation was to add 3 lots of row 1 to row 3. And the third operation was add 1 lot of row 2 to row 3. So E1 is this, E2, and E3. Okay, so if I put them in reverse order and then multiply it by A, that will give me U. Well, U was just what was left over after applying row operations. So that's kind of, don't bother, I don't need to multiply those together. With L, what you do is you take E1, invert it. I take E2, invert it, and take E3 and invert it. Okay, so I'm going to have to multiply 3 by 3 matrices together. Now, the beauty of elementary matrices are that this is going to be in identity matrix with the element in the second row, first column, that is just 2. This is identity matrix with the element in the third row, first column, is just -3, and similar for this one. So when I have to multiply these together, okay, all I get is second row, first column is 2. Third row, first column is -3. And third row, second column is just -1. Okay, that's my L matrix. Notice all of the main diagonals on the L, so all the values on the main diagonal on the L are all 1s. If you haven't got that and you've got some numbers up here on the L, you know you've gone wrong somewhere. Okay, so that's my L and U. If I test it and multiply those two together, I get back to my matrix A. Okay, so that's LU factorization. And I've got another one of these worked examples to go through on page 89. Before I forget, I just hand the sign sheet. Okay, so we're going to have a look at a couple of these examples. So first is 2 by 2, so I only need one row operation. Okay, so the operation I use is row 2 minus 5/2 row 1. So that gives me 2, 3, 0. 5 over 2 times 3 is 15 over 2. Minus 1 minus 15 over 2 minus 17 over 2. Okay, so one row operation required, and I'm already at row echelon form. So that's my U matrix. Okay, upper triangular matrix. So that was A21 minus 5 over 2 multiplied by A. Okay, because there was only one elementary matrix, L is quite simple. That's the inverse of what I applied to A. Okay, so U is my upper triangular, L is my lower triangular. Okay, and that's the LU factorization. If you want to know whether you got it right, just multiply L and U together. So if I do that, okay, so multiply those two together. Well, top row is just going to be 2, 3 because multiply 1 and 0. Bottom row is going to be 5 over 2 times 2 plus 1 times 0, which is 5. And 5 over 2 times 3, which is 15 over 2, minus 17 over 2, which is minus 2 over 2, which gives me minus 1. And that equals A. So that's LU factorization. Quite easy when it's a 2 by 2 because you only need one operation. Okay, what about a 3 by 3? Okay, I'm going to zoom out slightly here. I'll leave that there. 3 by 3, I'm going to need probably at most 3 operations because I need to reduce those 3 values there to 0. Okay, so if we do the same thing, same process. Okay, so what I'm going to do is add row 1 to row 2. And I'm going to add 4 lots of row 1 to row 3. Okay, so that will give me same top row. 0's underneath the pivot element. So what have I got? Minus 2 add 3 is 1. 1 minus 2 is minus 1. 4 add 12 is 16. Minus 3 take away 8 is minus 11. Okay, so got to get rid of 16. So I take away 16 lots of row 2 from row 3. Oh, hang on, got overzealous there, writing that down. So that'll be 0. So minus 16 times minus 1 is plus 16, so minus 11, so that'll be plus 5. So I've got a bit overzealous there. Okay, so that's my row echelon form. Okay, lower triangular matrix. Okay. So what we have here is we have U. Okay, so U is the reverse order in which they were applied. Okay, so reverse order, the last thing I did was row 16 lots of row 2 to row 3. Oh, sorry, minus 16 lots of row 2 to row 3. Then I did 4 lots of row 1 added to row 3. and 1 lots of row 1 added to row 2. And that's multiplied by A. And that gives me our upper triangular. You don't really need to write it out again, but why not? Okay, so the reason I write that, even though I calculated U here, I write it out like this because it just makes it easier to then calculate L. So L, okay, so take in reverse order. So I'm going to find the inverse of A211, which is A21 minus 1. Okay, take the inverse of A314, which is A31 minus 4. And take the inverse of A32 minus 16, which is A32 plus 16. Okay. Again, the good thing is these numbers in the subscripts gives us the element number or element location of the numbers in the bracket. Okay, so we know it's going to be like that. Okay, so it's 1's on the main diagonal and 0's on the upper triangular. Okay, so A21 was minus 1. A31 minus 4, and A32 was 16. Okay. Multiply those two together, you should get back to B. Okay, so it's quite a simple process. Row operations, your U is the row operations done in reverse multiplied by A. Your L is the row operations done in order but inverted. And that gives you your L and U. Everyone okay with that? It takes practice to immediately go, immediately see what these values are. But after a while, it's dead easy. Some authors, by the way, be aware, some authors reverse the 3 and the 2 here, and I don't understand why they do it, because it makes it harder when we go down to this stage, and it also follows naturally. If you write it like this, that R2 plus R1 gives us A211. But I don't understand it. Sometimes you may read textbooks where they reverse that. Okay. In my opinion, that's just overcomplicating things. Okay. Okay, so we've got around about 10 minutes left. That's what we just did. Okay, in the second lecture, what I'm going to do is show you why we've done this. Why are we calculating LU factorization? But I want to show you another way of doing it. And the reason I'm showing you another way of doing it is this is fine, what we've been doing for small matrices. Normally, we'll have large systems. You'll have 100 by 100 systems. Because elementary matrices, most of those numbers are going to be 0. That's wasted memory. That's wasted effort. Okay, so there is an algorithm which can calculate LU factorization, and it's called Krauts algorithm. Now, I've given you the derivation in the notes, so I'm not going to go through that. But essentially, what you do is you go down each column at a time. Okay, you take it a column at a time. And for the upper triangular elements, you calculate this. Okay, so Aij is the matrix A. Okay, that's the one which you're trying to calculate LU factorization for. L and U, these will already be calculated. For the first column, okay, these are easy. As we go through the algorithm, these would already been calculated. And L is given here. By the way, in an exam, I'll give you that. You don't have to remember this, so don't worry about that. Or I might ask you to derive it. You never know. Okay. The derivation of this is just you create an L matrix and a U matrix of unknowns, and then you just equate the A's to the L's and the U's. It's not difficult. Okay, so that's Krauts algorithm. Okay, so we got the same matrix as before, but this time I'm going to use Krauts algorithm to calculate the LU factorization. So essentially, we're going to keep referring back to these two equations. Okay, first column. So you take a column at a time. So when j equals 1, because j is the column number, okay, u11, so uij, so I is 1, j is 1, is aij, so a11, and this summation goes from 1 to I minus 1. But I is 1, so therefore that summation just disappears. Okay, so U11 is simply A11. By the way, the top row of your U matrix is always the top row of the A matrix. Okay, it makes it easier. Okay, L21. So this time I is 2, J is 1. Okay, because it's a lower triangular element, we don't bother with calculating the U because obviously it's going to be 0. Okay, L21 will be 1 over U11 because J is 1, multiplied by A21 and this summation. But this summation, when J is 1, will just disappear. Okay, so that's 1 over U11 times A21. U11 was 1, so we just got A21, which is 2. And similar for A31, which is minus 3. Lower triangular elements of zeros of U are zeros, and upper triangular elements of L's are ones and zeros. Okay. That's the first column done. Second column. Top row of U is simply the top row of A, so U12 is just 3. Okay, U22. Okay, I'm going to have to go back to the equation here. This time I've got I is 2, J is 2. So I've got A22 minus, so we have a single term in the summation. So K is going to be 1. So it's L21, U12. Okay, L21 times U12, that's 2 and 3. Okay, so A22 gives me minus 10. L32, okay, is 1 over U22 times A32 minus LIKUKJ. So I is 3. Okay, guys. J is 2. And essentially, it's just about plugging in those values, doing the summation, and it's kind of like a robotic manual process, really. Do the same with the third column. Okay, and then your L and U matrices, all the values are given here. Okay, so that's Krauts algorithm. We don't really use elementary matrices for anything over 4x4. It would just take too long. Krauts algorithm, a lot more efficient, and it's easier if we want to code it up. For example, in MATLAB. Okay, and I'm going to leave the worked example for the second lecture.
What operation is using?
In Krauts algorithm, there's no elementary operations, no. Okay, sorry guys, we just got a question. The question was asked, what row operations are we using in Krauts algorithm? We're not. We've replaced row operations by these summations here. These come from, yeah, so we're not using any row operations.
No, if somebody wants to prove that, how do you prove that?
Okay. If I just bring up the... Okay, there's the proof. Sorry, guys, I just want to just take care. I just want to show you very briefly what the proof is. There's your A matrix. That's your L matrix. That's your U. So all I've done is multiply them together, and there's a pattern here. Can you see? So that's where the pattern emerges. Okay. Sorry then. Okay, that's done. Okay, I'll see you in the second lecture later on.
Oh, just just determining the coefficient and finding the score.
Yeah. So essentially, yeah, if you go through, you can see there is a pattern emerging in the summation.
John, just a couple of questions. Into your report tomorrow, does it need an abstract?
No.
No, good. The other thing, I've sort of laid it out just like the template online, so sort of what I've done so far, what's left to be done. Is that sort of how it's supposed to be? Yeah, that's all right.
It's not something I want you to lose any sleep over.
Yeah, well, I've done it anyway.
It's kind of an exercise to get you sort of, get you into terms of it.
Yeah, all right, no worries. And put one on, turn it in online, and then print one off and give it to you.
The link should be online now.
Yeah, so if I do that tomorrow, I won't see you tomorrow, I don't think. Do I have to give it you tomorrow? Or
Thursday?
Yeah.
Friday will be fine.
Yeah.
Is it Thursday or Friday we meet?
Friday, I think. Yeah, Friday. Oh, in fact, we have a project meeting on Thursday, actually. So I can bring it to you on Thursday.